let's go into this unification, the battle against the contradictions and the tensions between the theories of physics. What is quantum gravity? Maybe what is the standard model of physics? What is quantum mechanics? What is general relativity? What's quantum gravity? What are all the different unification efforts?
Okay, so
Again, 5 questions.
yeah, it's a theory that describes everything with astonishing accuracy. It's the most accurate theory in the history of human thought. Theory and experiment have been successfully compared to 16 decimal place. We have that stenciled on the door where I work. It's an amazing feat of the human mind. It describes the electromagnetic interaction, unifies the electromagnetic interaction with the so-called weak interaction, which you need some good tools to even view the weak interaction. And then there's the strong interaction, which binds the quarks into protons. And the forces between them are mediated by something called Yang-Mills theory, which is a beautiful mathematical generalization of electromagnetism, in which the analogs of the photons themselves carry charge. And so this, the final piece of this, of the standard model, everything in the standard model has been observed, its properties have been measured. The final particle to be observed was the Higgs particle, observed over a decade ago.
Well, Higgs is already a decade ago.
I think it is, yeah.
Wow, time flies.
But you better check me on that, yeah.
That's true, but so much fun has been happening.
So much fun has been happening. And so that's all that's all pretty well understood. There's some things that might or might not around the edges of that, dark matter, neutrino masses, some sort of fine points or things we haven't quite measured perfectly and so on, but it's largely a very complete theory, and we don't expect anything very new conceptually in the completion of that.
Anything contradictory by new? Because
anything contradictory? Yeah.
I'll have some wild questions for you on that front. But yeah, anything that because there's no gaps. It's so accurate, so precise in its predictions. It's hard to imagine something.
Yeah. And it was all based on something called let me not explain what it is. Let me just throw out the buzzword. Renormalizable quantum field theory. They all fall in the category of renormalizable quantum field theory.
I'm going to throw that at a bar later to impress the girls.
Good luck.
Thank you. All right. So
they all fall under that rubric. Mm-hmm. Gravity will not put that suit on. So the force of gravity cannot be tamed by the same renormalizable quantum field theory to which all the other forces so eagerly submitted.
What is the effort of quantum gravity? What are the different efforts to have these two dance together effectively, to try to unify the standard model and general relativity, any kind of model of gravity?
Sort of the one fully consistent model that we have that reconciles that sort of tames gravity and reconciles it with quantum mechanics is string theory and its cousins. And we don't know what, or if in any sense string theory describes the world, the physical world, but we do know that it is a consistent reconciliation of quantum mechanics and general relativity, and moreover, one which is able to incorporate particles and forces like the ones we see around us. So it hasn't been ruled out as an actual sort of unified theory of nature, but there also isn't in my view, some people would disagree with me, but there isn't a reasonable possibility that we would be able to do an experiment in the foreseeable future, which would be sort of a yes or no to string theory.
Okay, so you've been there from the early days of string theory. You've
Right.
seen its developments. What are some interesting developments? What do you see as also the future of string theory? And what is string theory?
Well, the basic idea which emerged in the early 70s was that if you take the notion of a particle and you literally replace it by a little loop of string, that strings are sort of softer than particles.
What do you mean by softer?
Well, if you hit a particle, if there were a particle on this table, a big one, and you hit it,
Yeah.
you might bruise yourself.
Sure.
But if there was a string on the table, you would probably just push it around.
Mhm.
And the source of the infinities in quantum field theory is that when particles hit each other, it's a little bit of a jarring effect. And I've never described it this way before, but it's actually scientifically accurate. But if you throw strings at each other, it's a little more friendly. One thing I can't explain is how wonderfully precise the mathematics is that goes into describing string theory. We don't just wave our hands and throw strings around, and there's some very compelling mathematical equations that describe it. Now, what was realized in the early 70s is that if you replace particles by strings, these infinities go away, and you get a consistent theory of gravity without the infinities.
Mhm.
And that may sound a little trivial, but at that point, it had already been 15 years that people had been searching around for any kind of theory that could do this. And it was actually found kind of by accident. And there are a lot of accidental discoveries in this subject. Now, at the same time, it was believed then that string theory was an interesting sort of toy model for putting quantum mechanics and general relativity together on paper, but that it couldn't describe some of the very idiosyncratic phenomena that pertain to our own universe, in particular, the form of so-called parity violation. Our world is
another term for the bar later tonight.
yeah.
Parity violation. Okay.
So if you go to the bar and
I already got the renormalizable quantum
and you
field
look
theory.
in the mirror across the bar,
Yes.
the universe that you see in the mirror is not identical. You would be able to tell if you show the lady in the bar a photograph that shows both the mirror and you.
There's a difference.
If she's smart enough, she'll be able to tell which one is the real world and which one is you. Now, she would have to do some very precise measurements. And if the photograph was too grainy, it might not be possible. But in principle, it's possible.
Why is this interesting? Why is it? Does this mean that there is some not perfect determinism, or what does that mean? There's some uncertainty?
No, it's a very interesting feature of the real world that it isn't parity invariant. In string theory, it was thought could not tolerate that. And then it was learned in the mid-'80s that not only could it tolerate that, but if you did things in the right way, you could construct a world out involving strings that reconciled quantum mechanics and general relativity, which looked more or less like the world that we live in. And now, that isn't to say that string theory predicted our world. It just meant that it was consistent, that the hypothesis that string theory describes our world can't be ruled out from the get-go. And it is also the only proposal for a complete theory that would describe our world. Still, nobody will believe it until there's some kind of direct experiment. And I don't even believe it myself.
Sure. Which is a good place to be mentally as a physicist, right?
Yeah.
Always. I mean, Einstein didn't believe his own equations, right? With the black hole. Okay.
Well, that one he was wrong about that. But he was wrong about that.
But you might be wrong too, right? So do you think string theory is dead if you were to bet all your money on
No.
the future of string theory?
I think it's a logical error to think that string theory is either right or wrong or dead or alive. What it is a stepping stone. And an analogy I like to draw is Yang-Mills theory, which I mentioned a few minutes ago in the context of standard model. Yang-Mills theory was discovered by Yang and Mills in the 50s, and they thought that the symmetry of Yang and Mills theory described the relationship between the proton and the neutron. That's why they invented it. That turned out to be completely wrong. It does, however, describe everything else in the standard model. And it had a kind of inevitability. And, they had some of the right pieces, but not the other ones.
Sure.
They didn't have it quite in the right context. And it had an inevitability to it, and it eventually sort of found its place. And it's also true of Einstein's theory of general relativity. He had the wrong version of it in 1914, and he was missing some pieces. And you wouldn't say that his early version was right or wrong. He'd understood the equivalence principle. He'd understood space-time curvature. He just didn't have everything. I mean, technically, you would have to say it was wrong. And technically, you would have to say Yang and Mills were wrong. And I guess in that sense, I would believe just odds are. We always keep finding new wrinkles. Odds are we're going to find new wrinkles in string theory. And technically, what we call string theory now isn't quite right. But
we're always going to be wrong, but hopefully a little bit less wrong every time.
Exactly. And I would, bet the farm, as they say.
Do you have a farm?
I say that much more seriously because not only do I have a farm, but we just renovated it. Before I renovated betting at the farm, my wife and I spent 5 years renovating it.
You were much looser with that statement, but now it really means something.
Now it really means something, and I would bet the farm on the guess that 100 years from now, string theory will be viewed as a stepping stone towards a greater understanding of nature. And it would, another thing that I didn't mention about string theory is, of course, we knew that it solved the infinities problem, and then we later learned that it also solved Hawking's puzzle about what's inside of a black hole. And you put in one assumption, you get 5 things out. Somehow you're doing something right. Mm-hmm. Probably not everything, but you're there's some good signposts, and there've been a lot of good signposts like that.
It is also a mathematical toolkit, and you've used it. You've used it with Kamran Vafa. maybe we can sneak our way back from string theory into black holes.
Yeah.
What was the idea that you and Kamran Vafa developed with the holographic principle in string theory? What were you able to discover through string theory about black holes, or that connects us back to the reality of black holes?
Yeah. So that is a very interesting story. I was interested in black holes before I was interested in string theory. I was
Sure.
sort of a reluctant string theorist in the beginning. I thought I had to learn it because people were talking about it. But, once I studied it, I grew to love it. First, I did it in a sort of dutiful way. These people say they've claimed quantum gravity. I ought to read their papers at least. And then the more I read them, the more interested I got. And I began to see, they phrased it in a very clumsy way. The description of string theory was very clumsy and
Mathematically clumsy, or just the
mathematically
interpretation?
clumsy.
Okay, got it.
It was all correct, but mathematically clumsy. But it often happens that in all kinds of branches of physics that people start working on it really hard, and they sort of dream about it and live it and breathe it, and they begin to see inner relationships, and they see a beauty that is really there. They're not deceived. They're really seeing something that exists. But if you just kind of look at it, you can't grasp it all in the beginning. And so our understanding of string theory in 1985 was almost all about weakly coupled waves of strings colliding and so on. We didn't know how to describe a big thing like a black hole in string theory. Of course, we could show that strings in theory in some limit reproduced Einstein's theory of general relativity and corrected it, but we couldn't do any better with black holes than before my work with Qumran. We couldn't do any better than Einstein and Schwarzschild had done. Now, one of the puzzles, if you look at the Hawking's headstone and also Boltzmann's headstone, and you put them together, you get a formula and they are really central equations in 20th century physics. I don't think there are many equations that made it to headstones. and they're really central equations. And you put them together and you get a formula for the number of gigabytes in a black hole. Now, in Schwarzschild's description, the black hole is literally a hole in space, and there's no place to store the gigabytes. And it's not too hard and this really was Wheeler, Bekenstein, and Hawking, to come to the conclusion that if there isn't a sense in which a black hole can store some large number of gigabytes, that quantum mechanics and gravity can't be consistent.
We got to go there a little bit. So how is it possible? When we say gigabytes, so there's some information. So black holes can store information. How is this thing that sucks up all light and is supposed to basically be super homogeneous and boring? How is that actually able to store information? Where does it store information? On the inside, on the surface?
Yeah.
Where's?
Yeah.
And what's information? I'm liking this. Ask 5 questions to see which one you actually answer.
Oh, okay.
I'm
so
gonna
did
ask
you
you a
say
bunch
that
of-
I should try to memorize them and answer each one in order, just to answer them?
No, I don't know. I don't know what I'm doing. I'm desperately trying to figure it out as we go along here.
So Einstein's black hole, the Schwarzschild black hole, they can't store information. Stuff goes in there and it just keeps flying, and it goes in the singularity and it's gone. However, Einstein's theory is not exact. It has corrections. And string theory tells you what those corrections are. And so you should be able to find some alternate way of describing the black hole that enables you to understand where the gigabytes are stored. So what Hawking and Bekenstein really did was they showed that physics is inconsistent unless a black hole can store a number of gigabytes proportional to its area divided by 4 times Newton's constant times Planck's constant.
And that's another wild idea. You said area, not volume.
Exactly. And that's the holographic principle.
The universe is so weird.
And that's the holographic principle.
That's called the holographic principle, that it's the area. We're just jumping around. What is the holographic principle? What does that mean? Is there some kind of weird projection going on? What the heck?
Well, I was just before I came here writing an introduction to a paper, and the first sentence was the as yet imprecisely defined holographic principle. Blah, 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 blah.
Nice.
So nobody knows exactly what it is, but roughly speaking, it says just what we were alluding to, that really all the information that is in some volume of space-time can be stored on the boundary of that region.
So this is not just about black holes, it's about any area of space-time.
Any area of space. However, we've made sense of the holographic principle for black holes. We've made sense of the holographic principle for something which could be called anti-de Sitter space, which could be thought of as a black hole turned into a whole universe. And we don't really understand how to talk about the holographic principle for either flat space, which we appear to live in, or asymptotically de Sitter space, which the astronomers tell us we actually live in as the universe continues to expand. So it's one of the huge problems in physics is to apply or even formulate the holographic principle for more realistic. Well, black holes are realistic; we see them, but in more general context, to give a more general statement of the holographic principle.
What's the difference between flat space and asymptotic de Sitter space? So flat space is just an approximation of like the world we live in. So like de Sitter space, asymptotic. I wonder what that even means. Meaning like asymptotic over what? Okay,
so for thousands of years, until the last half of the 20th, until the 20th century, we thought space-time was flat.
Can you elaborate on flat? Well, what do we mean by flat?
Well, like the surface of this table is flat. Let me just give an intuitive explanation. Surface of the table is flat, but the surface of a basketball is curved. So the universe itself could be flat, like the surface of a table, or it could be curved like a basketball, which actually has a positive curvature. And then there's another kind of curvature called a negative curvature. And curvature can be even weirder because that kind of curvature I've just described is the curvature of space. But Einstein taught us that we really live in a space-time continuum, so we can have curvature in a way that mixes up space and time. And that's kind of hard to visualize.
Because you have to step, a couple of dimensions up? So it's hard to...
You have to step a couple... But even if you have flat space and it's expanding in time, we could imagine we're sitting here, this room, good approximation, it's flat, but imagine we suddenly start getting further and further apart. Then space is flat, but it's expanding, which means that space-time is curved.
Ultimately, it's about space-time. Okay, so well, what's de Sitter and anti de Sitter space?
The three simplest spacetimes are flat spacetime, which we call Minkowski spacetime, and negatively curved spacetime, anti-de Sitter space, and positively curved spacetime, de Sitter space. And so astronomers think that on large scales, even though for thousands of years we hadn't noticed it, beginning with Hubble, we started to notice that space-time was curved. Space is expanding in time means that space-time is curved.
Mm-hmm.
And the nature of this curvature is affected by the matter in it, because matter itself causes the curvature of space-time. But as it expands, the matter gets more and more diluted. And one might ask, when it's all diluted away, is space-time still curved? And astronomers believe they've done precise enough measurements to determine this. And they believe that the answer is yes. The universe is now expanding. Eventually, all the matter in it will be expanded away, but it will continue to expand because, well, they would call it the dark energy. Einstein would call it a cosmological constant. In any case, in the far future, matter will be expanded away and we'll be left with empty de Sitter space.
Okay, so there's this Einstein's cosmological constant that now hides this thing that we don't understand called dark energy. What's dark energy? What's your best guess at what this thing is? Why do we think it's there? It's because it comes from the astronomers.
Dark energy is synonymous with positive cosmological constant. And we think it's there because the astronomers have told us it's there. And they know what they're doing.
And we don't know what the heck
it is. It's a really, really hard measurement, but they really know what they're doing. And we have no friggin' idea why it's there. Another big mystery. Another reason it's fun to be a physicist. And if it is there, why should it be so small? Why should there be so little? Why should it have hid itself from us? Why shouldn't there be enough of it to substantially curve the space between us and the moon? Why did there have to be such a small amount that only the crazy best astronomers in the world could find it?
Well, can't the same thing be said about all of the constants? Can't that be said about gravity? Can't that be said about the speed of light? Like, why is the speed of light so slow?
So fast.
So slow. Relative to the size of the universe, can't it be faster? Or no?
Well, the speed of light is a funny one because you could always choose units in which the speed of light is 1. We measure it in kilometers per second, and it's 186,000, or miles per second. It's 186,000 miles per second. But if we use different units, then we could make it 1. But you can make dimensionless ratios. So, you could say, why is the time scale set by the expansion of the universe so large compared to the time scale of a human life, or so large compared to the time scale for a neutron to decay?
Yes. Yeah. I mean, ultimately, the temporal reference frame here is a human life.
Maybe.
Isn't that the important thing for us descendants of apes? Isn't that a really important aspect of physics? Like, because we kind of experience the world, we intuit the world through the eyes of these biological organisms.
Absolutely.
I mean, I guess mathematics helps you escape that for a time, but ultimately, isn't that how you wonder about the world?
Absolutely.
That like a human life
times
only 100 years. Because if you think of everything, if you're able to think in, I don't know, in billions of years, then maybe everything looks way different. Maybe universes are born and die, and maybe all of these physical phenomena become much more intuitive that we see at the grand scale of general relativity.
Well, that is one of the, a little off the track here, but that certainly is one of the nice things about being a physicist is you spend a lot of time thinking about, insides of black holes and billions of years in the future. And it sort of gets you away from the day-to-day into another fantastic realm. But I was answering your question about how there could be information in a black hole.
Yes.
So Einstein only gave us an approximate description, and we now have a theory that corrects it, string theory. And now sort of was the moment of truth. Well, when we first discovered string theory, we knew from the get-go that string theory would correct what Einstein said, just like Einstein corrected what Newton said. But we didn't understand it well enough to actually compute the correction, to compute how many gigabytes there were. And sometime in the early 90s, we began to understand the mathematics of string theory better and better. And it came to the point where it was clear that this was something we might be able to compute. And it was a kind of moment of truth for string theory, because if it hadn't given the answer that Bekenstein and Hawking said it had to give for consistency, string theory itself would have been inconsistent and we wouldn't be doing this interview.
Mm-hmm. Wow. That's a very dramatic statement. But yes.
That's not the most dramatic thing.
I mean, but okay, that's very life and death. You mean like that because string theory was central to your work at that time? Is that what you mean?
Well, string theory would have been inconsistent.
Yeah, okay. So then
string theory would have been inconsistent.
But those inconsistencies can give birth to other theories, like you said.
The inconsistency, right? Something else could have happened.
Yes.
Yeah, it would have been a major change in the way we think about string theory and it was a good thing that, one supposition that the world is made of strings solves two problems, not one. It solves the infinity problem and it solved the Hawking's problem. And also the way that it did it was very beautiful. It gave an alternate description. So alternate description of things are very common. I mean, to take a simple example, this bottle of water here is 90% full. I could say it's 90% full. I could also say it's 10% empty. Those are obviously the same statement. And it's trivial to see that they're the same, but there are many statements that can be made in mathematics and mathematical physics that are equivalent, but might take years to understand that they're equivalent, and might take the invention or discovery of whole new fields of mathematics to prove they're equivalent. And this was one of those. We found an alternate description of certain black holes in string theory, which we could prove was equivalent. And it was a description of the black hole as a hologram that can be thought of, a holographic plate that could be thought of as sitting on the surface of the black hole, and the interior of the black hole itself sort of arises as a projection, or the near horizon region of the black hole arises as a projection of that holographic plate. So the two descriptions were the hologram, the three-dimensional image, and the holographic plate. And the hologram is what Einstein discovered, and the holographic plate is what we discovered. And this idea that you could describe things very, very concretely in string theory in these two different languages, of course, took off and was applied to many different many different contexts within string theory.